So I'm going to talk to you about the Born square. Elizabeth, did you hear about that too? No? Okay, so now at least you have something. Okay, so Born square is actually, if you Google or the Wikipedia, it actually has a name, thermodynamic square. Okay? And everyone has a different version. Actually, the one that I find in Wikipedia is different from what I draw. So I guess we are all different. Okay, so who is Born? And his name is Max Born. Okay, and this is the one that where the apex of, he lived through the classical thermodynamics, which is we're discussing now, to the another one, which is quantum mechanics. And he won the Nobel Prize, Nobel Physics Prize, in 1956, 54. Okay, so he must be a very, he's one of the really important figures. So what do you think about is, I'm writing this one more time. What kind of energy do we know, right? We know 4 energies, right? And I want you to remember writing in an alphabetical order. So which one comes first? A. G. H. And U, right? So those are the ones. So let's start with this. So the way that we write it is, you write a square, and you're going to use this 4 side as the one that you want to write an energy. And you start with alphabetically. A goes here, and you write it in a circular direction. So A, G, H, and U. Okay. And then I am going to write the one that is variable. So what kind of variable do we know?
T.
T, P, once again, volume, and entropy. I mean, this is a really cool, right? And then when you look at that, you need to choose each corner. You need to put a variable. And I mean, my way of cheating this is, this looks like a little base, right? Little container. So I'm going to put, this is a box. Okay, so that's my choice in the first corner. Once you have this, you naturally kind of choose the other 2 variables. Because what this one is saying is, A is related to volume and the temperature. Okay, what about the G? What is my choice for naturally for G?
Temperature and pressure.
Temperature and pressure, right? And what you have left over here?
Entropy.
Entropy. So that's all you got. So that's all you need. And then you do this. He made this arrow. So this is what is called a Born cycle. I mean, this is a version of Born cycle. Somebody has a different way of arranging it. But this shows how 4 different energies and 4 different variables are all related. And then see how I'm doing it here. So let me choose the first one. Well, let's choose the first one. Okay. So when I do that, dA, right? According to the Born cycle, essentially this one is, he's the one who kind of come up with this ways to easily write this one. But we don't need to use this one to get. dA is depending on these 2, right? So I'm going to write dV dt. Okay. And so the dV is related to pressure, right? So that's the pressure. Oh, sorry. Always getting wrong. So somebody write an arrow this way, this the other way. So if you do that, so that is your partners, right? That is your group. So but you need a P to go, and you are going against the arrow, so it will be a negative P. then what about this? That's against the arrow direction?
Negative.
Negative S. So let's do the G. So your partner is dp, dp. And then what am I looking at? dt need a S against the arrow direction, so minus S. And dp need a D in the same direction, so plus D. So that's a bond cycle that we just, you drive this one in the beginning. So let's do the H, DH. Once again, that's a DS, DP. They are following the same direction, so DP need a volume positive, DS need a temperature positive. So that's what I do. The last one, EU. EU is need a volume, entropy. The volume need against the P, so now minus P. This one is following the same arrow, so just a plus. So you got these four equation. Okay. So that's how you do. And then one extra thing that we're trying to say in this diagram is A is natural choice for this is a volume, temperature. You see the G is pressure and the temperature. H is the natural choice is entropy and pressure. U is entropy. So those are the one that. So now we got this exact information. Okay, that's the whole cycle. And this one is the second one is even funny. Okay, so number 2, 1 dash 2. 1 dash 2, 1 dash 2. So this one even does not have, this is, I invented it because I have also traveled with the Maxwell. And the one that I like to draw is this. So if you look at that, I'm drawing the wheel with 4 quadrants here. Okay, and let's look at the map. The Vermont is a VP, right? That's a state symbol, Vermont. What about Pennsylvania? Yeah, and then there's no southern Pennsylvania, but let's say there's southern Pennsylvania. So I'm going to put it this way. And then this is flipped, right? Vermont's supposed to be here. Okay? Pennsylvania is supposed to be the eastern side and the western side and the one. So I want to say this is a negative. So this is my cheat sheet for the Maxwell relationship. So what's that come about? So if you look at that, I can write round V, round P, keeping pressure constant. You can write that this way. And it's negative of S, P, keeping this one constant. So that's the first Maxwell relationship. And then what do? You turn the wheel. Right? So let's turn the wheel. What do you? I want to put S here. So let's take a turn. So S is now here. P goes here. P goes here. Volume goes here. Right? And then they switch the sign. Okay? But to make a quarter turn, you're gonna keep changing the sign. So this one is now I can write round P, keeping S constant, round V, round S, keeping pressure constant. So that's the one other relationship that you can. Remember the Vermont and some southern part of Pennsylvania, okay? With the flipped location, that's a negative sign. Using this wheel, you get the second Maxwell relationship. And all you gotta do is keep on rotating this, okay? Third one, you do. I'll put, yeah, T goes here, volume goes there, S goes here, P goes up, and this one now negative. By doing so, volume constant, S constant, and with a negative sign. So if you look up the textbook, those are I just derived those three Maxwell relationship, and the last one I have to do one more time. S V T P with a positive sign. That one give me that round S, round V. The temperature constant is plus P, keeping the volume constant. So those are the four Maxwell relations. Okay. So that is a table. There is a table here. Okay. So I go back to this concept again from using the Born square and this kind of wheel diagram to do. And some of the one is actually quite useful. Let's see this. This it actually turns out to be quite useful, one of the useful Maxwell relationships. If I want to know entropy change, when I change my pressure, keeping the temperature constant, right? This is same as, for me, volume change as a response to the temperature change, keeping the pressure constant with a negative sign. This is something that is easy to handle. This is something that probably you might want to, maybe you might not want to know, but some people might want to know, right? So this is one of the useful relationship. The other one is probably this one too, right? Entropy change and the volume change can be expressed on 3. Now we feel very comfortable with volume change, pressure change, temperature, right? But entropy is such an annoying factor that we have to deal with. But some of the Maxwell relationship can be used to drive it. In my class note, there is this way. So I will, yeah. Let me finish that up because this one shows that. So Born square is 1. I can keep this one for declaration. So let's say one of the relationship. This is an example. So 2. The example is pressure change, temperature change, volume. I think we are talking about the last one there. Is that right? Yeah. You see the last one there? That's this equation. I just rewrite it. And remember this one. We are essentially asking that what is your delta S? T is isothermal. Your initial volume to final volume. Do you remember this? And you just took the quiz on this. What is the delta S is NR natural law. That's the old-fashioned way. You use isothermal means delta T is 0, delta U is 0, and you use a work Q reversible is a minus work reversible, stuff like that, and then divide by T. So you got to get this equation. I think I got it right. But you look at this second one. If I look at that, that's an isothermal volume change, right? So I can use this equation. Delta S is essentially pressure change, temperature change, keeping the volume constant times dV from initial volume to final volume. Just I have just figured this one out. Right? I can do the second way. So that's the beauty of this, something like a physics kind of oriented. There are multiple ways to get the answers. And this is an example. So pressure is, if it is a gas, what is my pressure? V equal mRT. Okay? So I put that in and then do the differential to the, with respect to the temperature. Okay, this is done now. So this one is initial, final, volume, nR dV. Okay? Temperature is gone, so nR. And this is a constant, so it goes out. You got this, and you got this, the same answer actually. So it's the same method, and you know the more you go, you find that this equation is a lot more powerful. When you think about what about the you guys remember the van der Waals gas, right? I can plug that in. It's not, the equation is not as neat as this. It's an ugly equation, but I can do that, and I can calculate the delta S for something like real gas with interactions. I can do that. So this equation is a little bit more useful. You know, there's so much things about. I mean, quickly, myself at least, I'm learning out of steam for getting interest in delta S calculation, because it's something that is really related to what I want to know. I mean, people want to know equilibrium constant, equilibrium scenario, and also vapor pressure phase diagram. This one, entropy, is just a secondary tool, so we have to really focus our attention to this guy. Okay? And that's the one that we are getting at.